Hello, I'm Tyler Folsom. I want to tell you about automating micro vehicles. This talk is divided into three sections. In the first part, we'll give an introduction and general background on what kind of energy it takes to drive a vehicle. Secondly, we'll look at our solution, which is the MilliPod. And we will finish up by looking at what the implications are for this in the future. Would it be feasible to electrify all land transportation? The question is it possible to do so sustainably, or do we wind up burning coal in order to power our automobiles? When we have a heavy car that is 20 times more than the person that's carrying, that's not a sustainable situation, no matter where the energy is coming from. The situation isn't any better for a bus. You still have the same ridiculous ratio of vehicle weight to passenger weight on a bus, and buses do not get particularly good fuel efficiency. Compound that with, in the United States, the average bus occupancy is only 9 people. Hopefully Europe does considerably better than that. In the United States, people drive about 5 trillion kilometers every year. However, about 65% of that is urban, and the average urban trip is only 19 kilometers. Now, the speeds that cars typically travel in the cities are not that great, typically between 19 and 34 kilometers an hour. Bus or light rail doesn't do a whole lot better than that. The three principal uses for energy are to do heating and air conditioning for buildings, to supply power for industry, and to provide for transportation. Now, there are decent sustainable solutions for the first two, but transportation is a little more problematic since fuels have to be portable. The energy for transportation generally goes to gasoline for cars, diesel for trucks, and jet fuel for planes. Electric micro vehicles are a good solution to the energy problem, but they don't seem to be widely used throughout the world. Let's look at the physics of what it takes to move a land vehicle. The energy to move a vehicle consists of two parts. One part to overcome rolling resistance, and the second part to overcome aerodynamic drag. The energy to overcome rolling resistance is directly proportional to the velocity and the mass, but the energy to overcome drag does not depend on the mass of the vehicle, but is proportional to velocity cubed. So at lower speeds, the rolling resistance is more important, and at higher speeds, the aerodynamic drag becomes more important. For heavy vehicles such as automobiles, the rolling resistance dominates at speeds less than 55 kilometers an hour, and the aerodynamic drag takes over once we get above 55 kilometers an hour. When the vehicle is light, then you don't have that much rolling resistance to start out with, and the crossover point is at about 20 kilometers per hour. Now, let's drill in on a more detailed version of the energy to overcome rolling resistance. I had left out a couple of these terms in the previous slide, assuming that the slope was 0 and that the acceleration is 0. When you do have to go up and down hills, that's going to take more energy. When you do have to accelerate, you have stop and go, that's going to take energy. There is an energy penalty for stop and go, and having heavy wheels is also going to impose an energy penalty. Here is the more detailed equation for the energy to overcome drag. There are terms in here that we can control, such as the drag coefficient, how much we streamline, or the frontal area, or we can control how fast we're going. There are things that we can't really control, such as the mechanical efficiency of the transmission, because that's already about as good as it's going to get, And we can't control the air density and the wind speed unless we're going to build a hyperloop, and that's not going to work in the city. Next, let's look at the energy that it takes to move a heavy vehicle versus a light vehicle. If you have a car with a single person occupying it, you'll need 31 kilowatts to move one person at 50 kilometers an hour. With a bicycle, it takes only 1 kilowatt to move that person at the same speed. Of course, getting a bike to go at 50 kilometers an hour will require either that you are a professional athlete or that you have an electric helper motor. And for this talk, we're going to go with the electric helper motor. If you streamline a bike, the energy required gets even better, dropping to 0.2 kilowatts. In fact, highly streamlined bicycles, you're able to get up to 130 kilometers per hour just using human power. These are touted as being very efficient, but that efficiency is not based on fuel efficiency, which is pretty lousy. Even when you divide your fuel consumption by the number of people who are riding the bus, it's still not particularly good. The main efficiency of buses is the lack of congestion. Pictures show the amount of street that you need to carry 200 people in 177 cars, or the amount of space that you would need to pack those people into 3 buses. Now, packing people into 3 buses is a little not that common, because then you'd have 66 people per bus, usually not that full, and if they are, that gets to be uncrowded and not too comfortable. Micro vehicles are also going to decrease the amount of congestion that you have in the city. The efficiency of buses is mainly based on the multiplier, which is somewhat fictitious. It's maybe applicable when you really have a good transit system using buses, not so much otherwise. If we ever get to self-driving cars, they have a number of advantages. One of them is less congestion. It's expected that self-driving cars can reduce congestion in the city by a factor of 2 or more, since they're basically choreographing themselves and making more efficient use of the space they have on the roadway. But the main advantage of self-driving cars is safety. We're never going to have self-driving cars unless they are significantly safer than human drivers. If we can drop the traffic accident rate by a factor of 10, the lives will save not just the people driving the cars, but people outside the cars, such as motorcyclists, pedestrians, and bicyclists. If fully automated or partially automated vehicles can deliver on their promise of greatly reducing traffic accidents, it makes 2- and 3-wheel vehicles much more safe to get around the city. They become a real transportation option. The preferred city vehicle of the future might look more like an overgrown bike than a traditional automobile. There's no reason to suppose that the automobile as we know it is going to survive its encounter with becoming driverless any more than the carriage survived becoming horseless. This is what I mean by an overgrown bike. It looks like a small car. 72 kilograms is awfully light for a car, even though it's heavy for a bike. With automation, it is possible to build an entire urban transportation system around vehicles this size. We have completed our review of what it takes to design vehicles with minimal energy to use in the city. The next section is going to look at how we put that into practice and design an urban transportation system that can really minimize energy. We need to design a whole system, not just a vehicle. We need to eliminate stop and go so that the vehicle can go through at a constant 50 kilometers an hour. An efficient vehicle doesn't do any good if it's stuck in traffic. We need to streamline the vehicle, minimize frontal area, cut down the weight, and do what we can to minimize the rolling resistance. Systems should maximize people density on the roads and favor people over vehicles. The solution is the MilliPod, which is a platoon of 2-person, fully automated electric micro vehicles. They follow a lead vehicle that's driven by a bus driver. The passenger pods are fully automated within a strictly limited operational driving domain. The MilliPod picks up passengers on the fly, never needs to stop at bus stops. The pods fit into a half lane, so we divide a standard lane into 2 half lanes. They would come to a bus stop, pay their fare, and select a destination. The passenger pod doors would then unlock, the rider would be seated, and wait for the platoon to come along. When it comes along, the pod pulls out into the acceleration lane, accelerates, and then will couple onto the rear of the platoon. It maintains its position until the destination comes, at which point it decouples from the other pods, moves into the deceleration lane, and comes to a stop.
Folsom, founder of MicroAV.
And I'm Matthew Muscola, electrical engineer.
MicroAV is about to disrupt the transportation industry by introducing the MilliPod.
The MilliPod moves people, not just vehicles.
It is a train of 2-person, fully automated electric micro vehicles that follows the bus driver's pod.
These vehicles will never need to stop. They'll be able to pick up passenger pods on the fly.
Here's the concept.
In this 3D rendition of the MilliPod system, we see a platoon of vehicles traveling in its designated outer half lane. Red pods represent those commuters joining or detaching from the system, using the inner half lane to maneuver without affecting the other vehicles in the platoon. MicroAV is actively working on the MilliPod system. We are looking for strategic partners and are interested in feedback from the community and transportation planners.
More energy efficient is the MilliPod. We have a weight savings that gives us a factor of 2 to 5 times over the bus. The wheels are more efficient by a factor of 2.5 times. When you multiply those two together, we get a energy reduction of a factor between 5 and 12. It's more than that. The stop and go is a big energy penalty for the bus. The whole bus needs to stop at every bus stop. For the MilliPod, only a few of the passenger pods need to stop, and the avoidance of stop and go at bus stops gives us an additional energy factor of about 18. Let's turn our attention to the drag side of the energy equation. The drag coefficient for a bus is 0.6 to 0.8. A really streamlined MilliPod can get that down to a factor of 0.12. Let's settle for more of the automotive range of 0.25 as a drag coefficient. That's 3 times better than the bus. Since the MilliPod has less frontal area, the bus has 4 times as much frontal area. The total aerodynamic drag on the MilliPod is going to be 12 times less than that on the bus. No stops for passengers. A MilliPod can cover a bus route 50% faster. This means that drivers will be able to cover more routes in the same amount of time, thus providing more frequent service. COVID-19 has really decimated transit. With the MilliPod, a person has their own private space and doesn't have to share space with a stranger or breathe someone else's air. It is renting the whole pod and can choose to share it or not. Pulling off bumper-to-bumper platooning is going to take some effort. It takes a very good control system. Are aided by a mechanical system that lets the springs in the bumpers absorb any minor mismatches in energy. Force on the physical couples between vehicles is kept to close to 0. We depend on good navigation, knowing exactly where our location is, and we're able to share that information between the vehicles in real time so that we can have precise relative maneuvers between the vehicles. Are using a fleet of scaled model vehicles to test the MilliPod control system, and we have automated 3 full-scale tricycles. Finally, let's look at where automated micro vehicles can go beyond the MilliPod. The base design for the MilliPod just covers bus routes. It does nothing for the first or the last kilometer. It will be quite easy to change this and equip the passenger pods with user-operatable controls so that the pods can be driven manually and then operated the way you would for a bus share or a car share. A person could use the pods the same way they would as a bike share, except that when they get to a bus route, they can wait at a stop and then join a MilliPod as it goes by and not have to drive in the main part of their trip. MilliPod is designed to run entirely off renewable energy. The pods use a 20-kilogram battery, which is good for a 30-kilometer range, which will handle most urban trips. When the pod's battery gets low, it will take itself to a bus stop that enables battery swap and swap out the battery and be back on the road again in less time than it takes to fill a gas tank. A bank of batteries that need to get recharged at any particular time that can be recharged when there is wind or solar available is very synergistic with enabling these forms of renewable energy. Some point in the future, entirely self-driving vehicles will become practical. When this happens, the lead pod for the MilliPod is no longer needed. We don't need the driver, so the whole system can go completely self-driving. Passenger pods can change into self-driving taxis and take their occupants anywhere without needing the bus lane. They can still couple together to reduce traffic, and the narrow width of the MilliPod further is going to reduce traffic. The impact of this is that in the United States, there's about 1.6 trillion kilometers of trips every year that are suitable for micro-taxis. If this switch to micro vehicles were made, that would account for 32% reduction in energy, which comes out to 43 coal trains every day in the United States alone. We're expecting similar results around the world.